Good morning, AP Chem students. Today we're going to be looking at the 2018 FRQs from the AP Chemistry test, starting with number 1. Number 1A specifically talks about the oxidation number in NaOCl, but let's put this in the full context. It says that a student performs an experiment to determine the value of enthalpy change, delta H standard reaction, for the oxidation reduction reaction represented in the balanced equation below. Okay, redox reactions are very much a focus of Unit 9, but we do briefly talk about them in Unit 4 of the AP test, so this might be a little bit of review. The first question says, determine the oxidation number in NaOCl. When you talk about oxidation numbers, you gotta look at each element and what their charge would need to be to add this all up to 0. So we take what we know are constants, and then we find our unknown. So in this case, it's asking what the Cl is, so we don't know what the charge is on Cl. So we look at everything else, and we know that all the charges have to add up to 0. Or all your oxidation numbers have to add up to 0. Remember, charges, oxidation numbers, largely the same thing. Now, oxygen is the easy one. It is almost always -2. Sodium is another easy one. It's in that 1A column all the way to the left of the periodic table. It's almost always going to be +1. Which means in this particular case, to make +1 and 2 minus balance out to be 0, this would also have to be +1, or just simply plus. Now, how does this make sense? How does this work? What's going on here? How does this make sense? Chlorine is a negative ion, we're typically taught. Well, if you look back at your periodic table, you'll remember that oxygen is up here, and then fluorine, and then below that you have sulfur and chlorine, kind of like this. In this case, because oxygen is more electronegative, because it's more grabby for your electrons, it's going to pull the electrons from the chlorine and make chlorine act as a positive ion. We see this more frequently with things like xenon tetrafluoride, where xenon, while a noble gas, will act as an electron donor due to its lower electronegativity, making it, in effect, positive. The second question is about the molarity required to make 0.5 molar sodium thiosulfate, or Na2S2O3. Notice how this question started talking about redox reactions and enthalpy changes, but the first two questions have very little to do with enthalpy. This has to do with redox, that you're talking about oxidation numbers, but that's about it. This has nothing to do. It's just a concentration. So please be careful that you don't write off a question right off the bat because you don't understand the initial language. Read through each problem individually, each section, and try to answer the ones you can. So let's go ahead. Calculate the number of grams Na2S2O3, or sodium thiosulfate, needed to prepare 100 milliliters of 0.5 molar sodium thiosulfate. Okay. What we are asking for is number of grams, but we don't have anything directly relates to grams. We don't have grams itself, and we don't have moles, but we have a way to get to moles, mainly through the molarity. So let's do the math out. We're making 100 milliliters because that's our end goal, what we're looking for. That's where I'm going to end up starting. 100 milliliters. Na2S2O3. And if it makes you feel more comfortable, you can put that over 1. Then we have this 0.5 molar. Well, 0.5 molar is moles per liter. So if I can have liters, I can find moles. So I need to translate this milliliters into liters. Once I have that, I can go to the next step, which is 1 liter Na2S2O3 is 0.500 moles. Okay, now that I have moles, how do I get to grams? Well, we can find the molar mass. Specifically, we can go, okay, how many sodiums do we have? How many sulfurs do we have? How many oxygens do we have? And what is the mass of each? And then multiply by how many we have. So let's go ahead and do that. Looking at our periodic table given to us by the AP Chem people, we find that sodium has a mass of 22.99. Sulfur is 32.06. And oxygen is 16.00. But we don't have one of each of these, we have multiples. So this would be times 2, times 2, times 3. Now, if you'd prefer, you can do each individual step out. You can go like 16 times 3 is 48, and so on and so forth. I personally just do it in one fell swoop, put it in my calculator with lots of parentheses. But if I do that properly, I should get 158.10 grams per mole. Provided you get this number, all you need to do is plug it in over here. 158.10 grams. Na2S2O3 is 1 mole. Sodium thiosulfate. And if you do this math out, multiply across the top, divide by everything on the bottom, you should get 7.90 grams sodium thiosulfate. That is A and B. Now on to C. C says, in this experiment, the student uses the solutions shown in the table below. We know that C is related to this information. It's not directly related to the previous questions because of this kind of break in the text. And it says that we use 0.5 molar sodium thiosulfate, 5 milliliters of it, and the amount we mixed up last time. We use 0.5 molar sodium hypochlorite. This is ClO or OCl. They're written this reverse of what we're normally used to seeing, but this is the hypochlorite ion. And we're using 0.5 molar and 5 milliliters of that. And then sodium hydroxide, again, 0.5 molar, 5 milliliters of that. Use the balanced equation for the oxidation reduction reaction. Okay, use the balanced chemical reaction and the information in the table above. Determine which reactant is the limiting reactant. Justify your answer. So, rephrase, restate, which one's going to run out first? Which one are we using more of per one time through the cycle? So let's think about this in terms of using a milliliter of a solution each time. It's not exactly accurate what's going on, but it'll help you get the picture. In this reaction, let's say for each coefficient, so like there's an applied 1 here, it'll use 1 milliliter. So it uses 1 milliliter of this, 4 milliliters of the sodium hypochlorite, and 2 milliliters of the sodium hydroxide per run. We only have 5 milliliters each, so in the first run through we use 1 milliliter of the sodium thiosulfate, We use 4 milliliters of the sodium hypochlorite and 2 milliliters of the sodium hydroxide, leaving us with 4 milliliters of the sodium thiosulfate, 1 milliliter of the sodium hypochlorite, and 3 milliliters of the sodium hydroxide. Now that we've done that, we can go, okay, wait, which one's running out first? We can just see that, visualize it. In fact, it might make it a little easier for me to put those numbers in. So let's give that a try. So we said for every 1 time through the reaction, we'll burn off a number of milliliters equal to the coefficient. So in the first run through, we'll burn off this 4, this 5. We'll use one of them because there's an implied 1 here, and leave us with 4. And this one will burn off 4, leaving us with 1. This one will burn off 2. 5 minus 2 is 3. And right now we can see which one's running out. Which one's going to run out first? The sodium hypochlorite is the closest to 0 after just one run through. Again, this is not strictly the best way to think about it or the strictly accurate way to think about it, but it is a very helpful way to think about it because these coefficients tell you the rate they're going to be consumed at. The higher the coefficient, the faster it's going to burn through. So in this particular case, whatever has the highest coefficient is going to burn out first because all these concentrations are the same, all these volumes are the same, which means we'll have the same number of moles. So if I'm burning through the sodium hypochlorite 4 times faster, I'm going to run out of it first. A justified answer might look something like sodium hypochlorite, or NaOCl, is the limiting reactant given the equal number of moles based on the concentration and volume of each reactant. It follows then that based on the coefficients in the balanced reaction, the NaOCl, or the sodium hypochlorite, will be depleted first because it's consumed at a higher rate, indicated by its higher coefficient. Switching back to the questions, D says all the solutions originally at 20.0 degrees Celsius are combined in an insulated chamber. The temperature of the reaction is monitored as shown by the graph below. According to the graph, what is the temperature change of the reaction? So here it starts at 20, and then as they mix, there is heat release. The water temperature goes up, and it goes up here to somewhere between these two lines. So somewhere between these two lines, the first is at 32, the second is at 34. This is 30, which implies that this line here in the middle is 33. So it's somewhere between 32 and 33, which we could say is 32.5, halfway between. And it really looks to be about halfway between. Remember, you can estimate 1 decimal spot past the last line you have, because this line goes to 1. This is 31, 32, 33, 34. The last decimal we have from our lines is the ones place, so we can estimate to the tenths. Then you need to find the difference. So it's 32.5 minus 20, or 12.5 degrees Celsius. And there we have it. E states that the mass of the reaction mixture inside the calorimeter is 15.21 grams. That's a useful number. I'm going to underline it right now. Given that number, calculate the magnitude of the heat energy in joules that is released during the reaction. Assume that the specific heat of the reaction mixture is 3.94 joules per gram degree Celsius, and the heat absorbed by the calorimeter is negligible. So, 2 very important things here. Tell me where I want to go. Heat and specific heat. There are only two things we've really done with either of these. But they both come back to this equation right here. Q equals M C delta T, or as I like to refer to it, the MCAT equation, because it's just how it sticks. This equation specifically refers to heat, which is the Q. M is mass, C is your specific heat, and delta T is your temperature. And we got the delta T from part C. Mass they gave to us, so this would be equals 15.21 times 3.94 times the 12.5 we found in the previous problem. If you multiply all these out, you will get 749 joules. That's it. That's all it's asking for. Really easy. Next one's the tricky one. Using the balanced equation for the oxidation reduction reaction and your answer to part C, which is misleading because E1 is more helpful. We'll get to that in a second. Calculate the value of the enthalpy change, delta H reaction, in kilojoules per mole. Include the appropriate algebraic sign for your answer. So what we need to do here is we need to go, okay, how many joules were released, which we have, is right here. We have 0.749 kilojoules per how many moles? Reaction. Which is a hard concept to understand, but we'll break it down. First, let's talk about the kilojoules. Remember, going between joules and kilojoules, just move the decimal 3 spots. If you prefer, you could also divide by 1,000, or you can do the full stoichiometric conversion, whatever your pick. The moles reaction is the harder part. We don't know how many moles reaction is. What that is how many times did the reaction complete? The best way to do that is figure out how many moles of your limiting reactant you have, and then you can go from there. So, in this case, we had 5 milliliters of sodium hypochlorite. And we know that it is 0.5 molar, which would be 0.500 mole per 1 liter, or 1,000 milliliters, which tells us that we had 0.00250 mole. Let's do this down here. Well, that's of NaOCl. If we go back to our original reaction, it takes 4 moles to make this reaction go once, or 1 mole of reaction. So that 0.00250 mole NaOCl, well, it's 4 mole NaOCl per 1 mole reaction. This will give you 0.0000625 mole reaction. Then you're going to divide this by this. And you should get, if you do the appropriate thing, 1.200, 1,200, which we'll want to reduce to the proper number of sig figs. So let's go ahead and write our answer down. We want to say in proper scientific notation with 1, 2, 3 sig figs is 1.20 times 10 to the third kilojoules per mole reaction. Now, here's the problem. Is that positive or negative? There are 2 ways to go about this. I'll go through both, but take whatever works for you. The first is to go, okay, originally the temperature went up of the reaction mixture is 749 joules, so that means the amount released by the reaction had to be negative 749. So the way this would be is that this would be negative all the way through, which would give us a negative answer at the end. The second is to do all the math by hand and then think about it afterwards. If the temperature of the reaction mixture went up, where did that energy came from? Well, it had to come from the reaction, which means the reaction gave up or was an exothermic reaction or emitted heat. If it goes down, well, that had to go somewhere. That energy clearly went into the reaction. It was absorbed. It was an endothermic reaction. Therefore, this delta H here would be positive. Whatever makes it make sense to you is the one you should go with, but the negative is important here. The scoring guidelines themselves say that if you do not have the negative sign, you do not have you miss out on one of the points. The number itself, the mole reaction here, is the first point. The second is for getting this with the negative sign. You're missing half the points on this problem if you don't think about the signs and pay attention to that in an endo or exothermic reaction. So do be very careful with that. F talks about if the student redid the experiment with twice as much volume, they do the entire exact same experiment, but with twice the volume of each of the initial reactants. The magnitude of the enthalpy change, or your delta H reaction, is the same as what you calculated in C or in E part 2. Explain this result. It's really simple. If we double the amount of reaction, we expect that the amount of heat will double. Okay? If you have 2 matches, they'll burn twice as long, kind of idea. So the amount of heat you have is doubled, but also the amount of things you reacted also doubled. So if you double your heat, or you double your MC delta T, and you double your amount, the ratio between them is still the same. This is what we calculated the first time. It hasn't changed. If you prefer a less mathematical answer, by doubling the volumes, you double the amount of moles, which means that you also double the amount of heat produced. Therefore, the amount of heat per mole stays the same, thus giving you the same results as the first experiment. The net ionic equation is slightly harder, but is still fairly easy as problems go. Just make sure you find where your positive and negatives are and split them up. So this is why we have you learn all your ions. So you can go, oh, right, so S2O3 is an ion, so that will split. Sodium and the hypochlorite, which is the only tricky part, will split. NaOH will split. I forgot the AQ tag on that. I'm so sorry. So will the... Oops, wrong color. So will the sodium sulfate and the sodium chloride. The only thing that doesn't split is the water because it's not aqueous. It is just a liquid. It stays right as it is. So, first things first, when you're writing an ionic, write the complete ionic, which is just everything that you had up top split apart into its ion form. So, let's go through that. 2 Na, 2 coming from here, plus aqueous, plus S2O3 2 minus, or thiosulfate, plus 4 distributes out, 4 Na plus 4 OCl minus, again, both aqueous, plus 2 Na plus aqueous plus 2 OH minus aqueous. If you're sick and tired of writing, me too. But this is very helpful for what we do next. Next, do the same thing on the product side. 2 times the 2 gives us 4. But I'll write it out separately. 2 times 2, which simplifies down to 4. Na plus AQ plus 2 times the number of sulfates we have. AQ plus 4 Na plus AQ plus 4 Cl minus AQ plus water. There we go. And remember, because water is a liquid, it does not split up. It stays just the way it is. Now, this is your complete ionic. Okay, all the ions represented, everything's there. To find the net ionic, you find your spectator ions and eliminate them. Your spectator ions, for memory's sake, is anything that shows up on both sides of the equation unchanged. So for instance, we have 2 and 4 and 2 makes 8 sodiums originally. Those don't do anything meaningful. They just are there hanging out. And how we know? Because on the other side, we have 4 and 4 sodiums, or a total of 8 that don't do anything. Any species that shows up on both sides gets canceled out. Once you found your spectator ions, rewrite for your net ionic without any of those present. And do remember your state emitter kind of tags. So S2O3 2 minus plus 4OCl minus plus 2OH minus. All these are aqueous. Gives me 2SO4 2 minus plus 4Cl minus aqueous plus water. A good way to check that your net ionic works and makes sense is check the charges on each side. Here we have a -2, 4 -1s, and 2 -1s. That gives us 2, 4, 8, -8. On the other side, we have 2 times 2, which is 4, or -4, and then another -4, -8, -8. Your charges should balance out if you're doing your net ionic carefully. And that is 2018 AP Chem number 1. Good luck.